Okay, welcome back. So in this last little section, we're doing mixing and matching all the things we've done before. So like you can see on the Epsilon Delta Explorer in Desmos, there are 5 types of locations for limits. There's the ordinary limit, there's left and right, and there's infinity and minus infinity. And each of those has a different meaning. So the ordinary one we know is like sliding around, getting close to x equals a. Left and right are getting close to x equals a, but only on one side, right? Only on one side. And being infinity or minus infinity is being either large enough, greater than n, or it's being small enough, less than minus n. And both of those they're all different types, right? And these are all different things you can do for the location. You can also do 3 different things for the value of the limit. So you can have the green zone can be getting close to y equals L, shrinking around a point, or you can be doing infinity, larger than something, or minus infinity, less than something. And so there's 5 possible places you could be going. There's 3 possible values you can get, and you can mix and match any of these. You can combine the x's and the y's in all the possible ways. So there's actually 15 possible limits that could happen. The classical epsilon delta is only one of them. And you can mix and match these 15 options in any way. So here are the definitions. Choose one option for where you are going. Where is the limit approaching? These are what the x values are doing. What are the x values doing? And there is a thing for what are the y values doing. And you can combine these things to get the definitions you need. So for example, let's do an example. Write down what limit as x goes to 3 plus of 1 over x minus 3 equals infinity. What does that mean? Well, a limit as x goes to 3 plus is a right limit. That's this line over here. This line, a right limit. So there's going to be a there exists delta. So a less than x less than a plus delta implies something. So let's write that down. There exists delta greater than 0. So a less than x less than a plus delta implies something. So this is saying when the x values are a little bit larger than a, but close enough, close within delta, then something is going to happen. And the other part is equals infinity. Let's look up what that means. That's this thing over here. And that means for all n greater than 0, this stuff, f of x, is going to be greater than n. Okay, I think when I did it earlier, I used m instead of n. But of course, it's perfectly legit. You can use any letter you want. As long as you use the same letter here and here, it's perfectly fine. So here it is with an n. I think earlier I said it with an m. But whatever you want, whatever floats your boat, whatever your favorite letter is, you can use there. So this is a perfectly good definition of this limit. And it's saying, no matter how big you want to get, as long as the x values are that close, but a little bit bigger than a, the x values have to be a little bit bigger than a, then f of x will be bigger than n. That's what it means. Okay. And you can do this in all sorts of ways. There's 15 possible ways. Example 15. Prove it. So now we're gonna go through this statement and prove it. And this was one of the limits we saw in week 1. So let's do it. So I'm given epsilon greater than 0, and I want to show that you can go from 1 over x minus 3. Oh, I guess I should. I did a stupid thing, which was that I wrote f of x, but I didn't fill in what the function is. So the function is 1 over x minus 3, and the a value is 3. So I gotta fill those in. 3 plus delta. Okay, now let's prove it. We're going to prove this statement. So we're going to prove 1 over x minus 3 is bigger than n. That's where we're going to start, and I would like to get to this thing. 3 less than x less than 3 plus delta, and I'm given an epsilon, or I'm given an n, and I want to find delta that makes this whole shebang work out. Okay, so I start out with 1 over x minus 3 and an n, and I want to get to an x. Why don't I do the reciprocal of both sides? Can I do the reciprocal of both sides? Are both sides positive? Right? To do the reciprocal, you got to make sure both sides are positive. N is definitely positive. N is bigger than 0. Is 1 over x minus 3 positive? The answer is yes. And the reason is, the hypothesis is that x is bigger than 3. if x is bigger than 3, that's the same as saying x minus 3 is bigger than 0. So, okay. Put in my lines correctly. That one if and only if that one. Because we're starting at x minus 3 bigger than 0, therefore we know that the 1 over x minus 3 over here will be positive. So it's okay to do reciprocal because we know 1 over x minus 3 bigger than 0 since x minus 3 bigger than 0. That's the hypothesis. Okay, so we can do the reciprocal to get x minus 3 less than 1 over n. When you do the reciprocal, the sign changes. And now I'm very close. Why don't I just add a line? 0 less than x minus 3 less than delta. If you're between 0 and delta, and if I set, I'm gonna be setting delta to be 1 over n. So I'm gonna set delta equals 1 over n. That's gonna be good. That's gonna be the thing that works. If you're between 0 and delta, so this is true, x minus 3 less than 1 over n, right? Like this. This line is the same as that line because delta is 1 over n. If you're between 0 and 1 over n, then you're definitely less than 1 over n. So this is all perfectly good now. The chain of logic works. All the steps are correct. I made sure when I did the reciprocal that both sides were positive. So this is a perfectly good proof, and you can see there's not as many things going on as the classic epsilon delta proofs, but you do have to be careful with the things that are going on. Okay, let's do one more. This is the last thing over here. Let's prove that the limit as x goes to 0 plus of ln of x is minus infinity. And what does that mean? So for a limit to be minus infinity, that means arbitrarily negative. So no matter how big a negative you want to get, the ln of x will be less than negative m. That's what it means. No matter what m value you give me, the ln of x will be less than minus m as long as we are close enough to 0. So there exists delta. So 0 less than x less than delta. It's a right limit, so x is always a little bit bigger than 0. That's going to imply ln of x less than minus m. So let's prove it. So let's start at the end, ln of x less than minus m, and I want to get to 0 less than x less than delta. How do I undo the log? I have a ln of x. How do I make it look like an x? I'm going to do the exponential of both sides. Exponential of both sides. You get an x over here, and you get e to the minus m on the other side. Okay, there's an important thing. X less than e to the minus m could include negative numbers, but ln of x does not include negative numbers. So if you want to go from this line to this line and make sure that they're exactly the same, you got to actually have this. X is bigger than 0, then ln of x will be less than minus m. And that's because of the domain of ln. Domain of ln. Let's call it ln x. Okay. And look, this is like beautifully set up to be what I want. All I got to do is set delta to be e to the minus m. So the proofs are actually usually pretty easy. Just the conceptual part maybe that's hard for these limits at infinity and mixed limits. Okay, that is it for this section. The other thing we skipped was the fundamental sign limit. That's going to be in the next video.